Good afternoon, everyone, and thank you for joining us for the AnalytiXIN Manufacturing Data Assets Research Seminar. Today's seminar is being presented by Dr. Wang from Notre Dame University, and I'll just let you take over and present your work.
All right, thank you. So let me first share my screen. So can you see my screen? Okay. All right, so good afternoon. My name is Jianxun Wang. I'm an assistant professor of aerospace and mechanical engineering from University of Notre Dame. So today I would like to basically present some of our progress of developing a physics integrated differentiable hybrid neural modeling for modeling the carbon-carbon composite manufacturing process. So this is a collaboration work with Honeywell and supported by AF4SR as well. So the motivation of this work is basically we talk with Honeywell, which is a manufacturing company that try to manufacture the carbon-carbon composite. So to produce the carbon-carbon composite, that goes through like many different manufacturing process, like the chemical vapor infiltrations, the rising, pitching, so that involves a lot of like complex physics. So it usually take a very long time for Honeywell to like develop the recipes to produce their product. So in general, if we want to optimize this manufacturing process and to like change the property of the materials, as if we rely on the experiment or just rely on their like real manufacturing process, and by tuning the knob, so the whole process is gonna take months. So it's not possible. And so we are trying to like model this process. But as you can see, this physics, it involves a very complex physics, and many of those underlying physics we may not fully understand. So how can we model this such a system? So luckily, like Honeywell, they have a lot of historical manufacturing data. So we start from like maybe we can use the data-driven models and to model this process. So basically, use a data-driven method like to model the manufacturing process. It's more like we're trying to learn the spatial temporal physics, because that involves a lot of spatial temporal physics. And in the in recent years, neural networks, like a more advanced, cutting-edge neural network, has shown a great promise to model the spatial temporal physics in the not necessarily in the manufacturing process, but like to learn the general spatial temporal physics. For example, like DeepMind has developed a model named Mesh GraphNet. So they have been published this work in iClear 2021, and they kind of try to use this graph neural network to learn the complex spatial temporal physics. You can see like the aerodynamics, the general like CFD, the computational fluid dynamics, flow structure, interactions, and solid mechanics. Okay, so from this animation, it's very impressive actually, because if you would like to do this completely based on numerical simulation, it's going to be very expensive, and their prediction agree with ground truth pretty well, at least visually. So we're interested in these directions. But the thing is, if we rigorously check the accuracy, okay, so we tested this Mesh GraphNet and on modeling the fluid dynamics, which is heavily involved in the heat transfer in the manufacturing process. So let's see if we want to use this model and to learn the spatial temporal transitions, and then we use this model and to roll out the model and start from some initial condition and make the predictions. So here we tested the models and to model, like to predict the complex vortex dynamics. And And this is what you're going to see. So at the beginning, the prediction is pretty good. But after a while, the error will be accumulated. Because this is like a next step model. So once you have a very long-term model rollout, eventually the error will be accumulated and completely dominant the prediction. So the result will become unphysical. So then what is the problem of purely data-driven models? So basically, it requires, because it's completely based on data, so it requires a lot of data. So it's data hungry, right? And also like you try to fit the data. In most of the case, they have a poor generalizability. Like what I have shown you, like if you roll out a model and to make the prediction, the forecasting the future, and if it change like the different Reynolds number, different modeling parameters, and it will have a pretty bad performance in general. That is because the issue of the complete, like a purely data-driven model, they have usually have the challenge for the generalizabilities. So for our problems, so there is a significant lack of the open literature data. So the data from Honeywell's, even though they have a lot of the manufacturing data, but if you look at the data in the high dimensional parameter space, they're pretty sparse, and the range of the data is narrow. So if we're going to use this data to train a model, and you're probably going to face like the extrapolation in the parameter space, and you're going to face the sparsity, very sparse data, and for training. So it basically won't work well, and also try to collecting more data is strictly time and resource consuming. So like I mentioned, try to conduct one set of the experiment take months. Okay, so but here is the thing that we are not completely blind to this manufacturing process, and we still have some prior knowledge about the underlying physics of the manufacturing process, which, however, might be like vague, uncertain, and sometimes there might be incomplete and inaccurate. So, for example, we know this whole process involved, of course, the mass should be conserved, energy should be conserved, right? So those mass conservation, energy conservation, the heat transfer, diffusion process, we know that involve those processes. But to accurately describe this process, you also need to know a lot of the constellations that are related to the chemical reactions. And there's a lot of unknown parameters. What is the chemical reaction rate for 100 species, right? And what is the constellations for the other to close this models? Sometimes we don't know, and sometimes we are relying on some heuristic models. And similar for the mechanical equilibrium equation. So this equation is true, but what is constellation for this complex fiber reinforced materials? Those are pretty vague. So the question is, can we leverage those incomplete and vague physics prior and to enable a better data-driven learning? So this is the focus of this talk. So we know people talk about the physics-informed machine learning. A lot of people have done this in the past few years. Like people are talking about how can we integrate the physics into the neural network. So the one possible way, or most people are talking about physics-informed, is they try to utilize the physics, which is the governing equations or some constraints, and put that into the loss function. So if you know the conservation law, like the mass should be conserved, so the violation of this conservation law should be considered. So the one way is, okay, I can basically put if I know the governing equations and I calculate the residuals, and I put the residual into the loss function and to constrain the neural network training. And this is a general idea of the physics-informed neural networks or PIN. So well, this PIN stuff. So basically, you actually treat all this like the physics and utilize that as constraints, as soft constraints, because you add a pattern term in the loss function, and It has problem because when you try to integrate those nonlinearity into loss functions, you're going to face a multiple loss component, and you try to optimize this neural network. And that multiple component, loss component will make the optimization very difficult. And there's a lot of literature, like people are trying to solve this, but there's still the challenge, like pain face. And another thing is, so basically, if you want to integrate or incorporate the physics into the loss function, you have to describe the equation residuals. That means you should know the complete form of the governing equation or constraints. But like I mentioned in the previous slides, if you don't know the complete form, if you just know, okay, this process is dominant by some diffusion and convection, but I don't really know like what is going on, and like there are some other relations I don't know. So how can you how can you construct any like residual or equation residuals? Those are not known, right? So we are trying to leverage those physics in a different way. So alternatively, we propose to integrate those vague physics, partially no physics, in terms of the PD operators, because all the physics can be described by partial differential equations, and we have incomplete model forms, and so we know like there's diffusion term, convection terms. So can we integrate those as a part of the neural network architectures? So basically, we leverage the partial no PDEs and to inform the neural network architecture design. So the rationale is based on the relationship between the PDE, the partial differential equations, or ODEs, and with the neural network architectures. So like I can make this concrete. I can give you some examples. So what is the relation between the neural network architectures and the partial differential and differential equations? So if you think about the residual connections or residual layers for which is the basic component for the REST net. And so the residual connections is based on the skip connections that describe the information propagation through the neural network layers, right? So if you write it out mathematically, so it's nothing but discretized version of the ODEs. So that means the trained residual connections can be interpreted as like certain discretization of certain ODEs. So on the other hand, you can use the ODE to define residual connections, so the continuous ODEs can be viewed as a residual connection with an infinite number of layers. And this is like the idea of the neural ODE. So people have used this relation to develop like the kind of a new neural network architectures where basically solve the ODEs and to propagate to achieve the residual connections, and that is known as the neural ODE. And then what about the convolutions? So the convolution is a building block for any like convolution neural network. So it can be related to the spatial differential operations. So if you try a convolution operators on the rectangular domains, so basically those convolutions can be interpreted as finite difference based spatial differentiations or differentiation operations on a uniform grid. And this idea, of course, can be extended to the non-Euclidean space and for the unstructured mesh. So basically, the graph message passing can be interpreted as discretized spatial differentiations on the unstructured grid. So that we can bridge the convolution or graph convolution with the PD operators, those diffusion, convection, and so on. So combine this, and we actually can bridge the PD and ODE with the the convolution residual networks or graph convolution residual networks. So basically, motivated by the relationship between the neural network architectures and PDs, like people in the deep learning community have leveraged those relations to design new neural network architectures. For example, people have leveraged the the property of the convection dominant PDEs, and to try to design the new deep graph neural networks and try to mitigate the over smoothing issues. And we know, like, if you have a lot of message passing and it goes, you're going to go through, like, you will have the over smoothing issues, and they try to leverage the convection PDEs and to overcome these issues. But for us, we are going to leverage, we're going to use the neural network and try to model the spatial temporal physics in the manufacturing process and in general. And we know, like, some underlying physics which can be described by the PD operators. So can we utilize those PD operators and blend that into the neural network? So kind of inform our neural network architecture design. So here I like to give you some examples. So how can we bake this physics into the neural network architectures? So the manufacturing process involved the spatial temporal physics, like heat transfer, chemical deposition, reaction, diffusions. So usually the sequence networks like recurrent, LSTM, and conv, LSTM transformer are very effective to model spatial temporal physics, right? To model the spatial temporal dynamics. Okay, so here I just plot a generic recurrent neural network structures. So here, instead of, like, unlike the classic black box or current recurrent neural networks where the recurrent unit is completely black box, okay, here we would like to design a physics-informed recurrent unit that try to integrate those PD operators which appears in the governing equations. So what we did is, okay, let's encode those PD operators. Like, if we know this process covered by is dominant by diffusion, convections, and sometimes pressure gradient, and we can encode those PD operators as a convolution residual connection, where the convolution filter is predetermined by the PD operators, and then we connected with the trainable, with the trainable parameters, and also with the trainable convolution, residual convolution layers, and in this way, and we can. One thing is to figure out how can we construct those PD operators, and also we can kind of use a trainable part to model the unknown physics, and at the same time, we want to speed up this like inference. So we would like to make everything on the coarse mesh, like coarse grade. So we have very fast inference speed, and we can go like a larger time step. So UT to UT plus 1 is not like the numerical time step. We can go across like 100 numerical time steps, for example. And then I have this physics integrated recurrent unit. So we want to test if it's good, if it's better than the black box one. So what we did is, okay, let's use this physics integrated or PD integrated recurrent unit. Let's try to learn some like the dynamic transition from the state T to T plus 1. And once we train these models, and then we can do the rollout and start from the given initial condition, and you can predict the physics in the futures, right? And we will decide the same structures, and this time we'll make everything like trainable. So this will be our black box baseline. So they have the same amount of training parameters and the same amount of like and similar structures. The only difference is this one I actually encode the PD operator. So the first test case, I'm just use this one like unit and try to train a model and learn the flow dynamics I've shown you in the previous slides, and I gonna evaluate this model in the next step manner. So I'm gonna like roll out this model. So I train this model and with different Reynolds number, and so I should introduce this flow a little bit. So you have the channel and you have a jet. So the position of the jet can change. Okay, so I can train this model with different jet position, different Reynolds number, and I test the models for on-seat Reynolds number and on-seat jet positions. Okay, so here I'm showing you two testing case. The first row is reference. Second row is PD integrated, is ours, and last row is completely like a purely data-driven black box baseline. And you can see at the beginning, the rollout is pretty good for both models, but after a while, like I mentioned, this time you can clearly see the arrow is going to be accumulated a little bit. So especially for the high notice number, the arrow accumulation is pretty fast, and you can see the phase and the physics completely gone. But compared to this one, our model by integrating the convection, diffusion, and pressure gradient, which is the building block for the Navier-Stokes, of course. So this agree with the reference very well, like even for the long-term rollout. So if you check out the model rollout arrows, basically here, this is the training range. So we only use the first 70 time step and for training, and then we do the rollout start from the very initial conditions. And remember, we also change to test the model for different parameters. So for testing, all the models actually are evaluated from just given the initial condition, and they will roll out to predict all the futures. So you can see this orange line represent the completed black box models, and the arrow goes up significantly. Remember here, this is relative arrow, so the arrow goes up to 100%. So it doesn't make sense. That is why you see the non-physical result in the long-term rollout. But if you check out our models, so this PD integrated models, it's pretty accurate, and you can barely see the arrow accumulation, and the arrow remains low. And also, interestingly, the uncertainty of the models. So the model for the purely complex black box, if you test it on the multiple different Reynolds number jet positions, and the variation of the arrow is huge, and you can see the scattering is huge. The model is not quite robust, but by introducing those physics, and the robustness of the models can be significantly improved. So this region, the blue region, actually represent the scattering of the rollout arrows. Okay, so we are pretty confident that by introducing those PD operators into the network structure will be significantly improve the performance of our model. So and this is one more test is the reaction diffusion, and we compare this our PD integrated neural networks and with other state-of-art neural operators like the FNO, the Fourier neural operators, and DeepONet. DeepONet with large parameters and also PIN. So the first column is ground truth, and the second is ours, and remaining is other state-of-art models. So you can see in the time. So the go down is the time directions. So for the long term, our models still pretty much capture the physics. But look at the other models, their predictions are dominated by arrows. And similarly, you can look at the training and testing rollout arrows. This is the horizontal axis is evolving time step, and the vertical is relative arrows. So the dashed line represent the training arrows, and the solid line it's not training arrows, it's like a test on the training set, and the solid line is the testing arrow, so the test on the on-sea parameters, on-sea initial conditions. They're pretty consistent for our model, right? But if you can look at other models, for example, FNO, it has a very good fading capabilities. So for training, it can go pretty low, and when it's go to extrapolation range, and it goes up. And if you look at their testing, meaning their model are tested on the on-sea parameters, so the testing error is order of magnitude higher, or even more than order of magnitude. So that demonstrates the generalizability of doing this, integrate the PDs into the network structures. So I also compare it with the memory footprint, inference cost, because, like I said, compared with the baseline model, so our models just have the similar trainable parameters, similar structure. So the inference cost is for sure is at least comparable to the baseline model, and much lower than the other neural operators learners. And for the memory footprint is also comparable. So But what we can gain is the better generalizability, robustness. So let's go back to this manufacturing process. Basically, I'm just showing like one PD integrated recurrent unit. So if we put them together as a sequence net, and so we developed this whole thing in a differentiable programming. We use JAX. So basically, everything is completely differentiable, and so we can build the loss and because the gradient can be backpropagated from the last step to the very beginning. So we can enable the sequence to sequence learning. So we can guarantee like the long sequence, the prediction is pretty stable. And at the same time, because we have those physical terms, so the parameters, the physical parameters like the diffusion coefficient or the other like reaction coefficient that associated with those PD terms can be inferred simultaneously because you can make those unknown parameters trainable. So this is a differentiable programming framework, and I'm going to use several like manufacturing process examples and to show you how well it will work. So for example, like in this carbon composite production, securing is a common step, and it's very critical actually. So because it transforming the loose mass of fibers and wrestling into the engineering composite materials. So this process actually involved the coupled physics of the heat transfer and the thermochemical reactions, and which could be very complex in the real world scenarios. So in general, in the state variables or state variables, we are interested in the degree of Q and also temperature, right? So for the temperature, like heat transfer, pretty confident about this whole process. It's covered by this diffusion process. But for the degree of Q is involved in thermochemical reactions. So this part in the real world, we probably don't know what it is. And it's hard to model. So here, let's assume that the curing kinetics is not known. But to test this model, we need to build a virtual environment. Later, I will show you like the real experiment. But here, let's see. We're going to use existing curing models as a ground truth, and so we can generate synthetic data and build our virtual like experimental environment, right? And even for this heat transfer process, we know like the governing physics and probably, but we don't know those spatial temporal coefficient or parameters like the thermal conductivities, the ultimate heat of reaction of the system, and convective heat transfer coefficient. Those are unknown. Okay, so then we will use this to use this like the ground truth model to generate synthetic data, and we validate our synthetic data with like the real experiment data. It's physical. Okay, and then we were going to use this model to generate data and to play with our data-driven model. So, like I mentioned, we kind of use the PD terms in this null physics, the heat transfer equations, and we assume that we don't know the pure kinetics, and we build this PINDIF model. So PINDIF model represent the physics or PD integrated neural differentiable models. Okay, and if I don't think I have a lot of time to go into those details, but if you're interested, we are going to publish this work. You can check out our publications. So the general idea is we just integrate those diffusion terms and some reaction terms, but we have a lot of unknown parameters, and we also have the unknown part, which is modeled by the trainable convolution neural networks. So to compare, to demonstrate the merit, and we also need to compare with the state of our other black box neural deep learning models. So like we use the neural PDs and autoencoding conv LSTM as other like black box space slice, because those are known to be very effective for modeling spatial temporal physics. So then we started to do some experiment. So let's collect the data. This is the composite. This is our sample, and we're going to collect the data like the temperature and degree of Q on this 5x5 sensors, and with one given oven temperature profiles. And then we will observe the degree of Q and temperature at this 25 locations. And then we train those 3 models. So PINDIF is our models and the other 2 black box baselines. So once we train this model, and the model can predict the temperature and degree of Q evolutions over time and for anywhere of the sample. So here I'm just showing you like at the center, the temperature evolution, the temperature time sequence, and this blue one is a temperature at the corner. So the blue solid curve is the oven temperature profile over time. So it's more like a boundary condition. Okay, so if you and this one is for degree of Q. So for all the 3 models, if you just tested for the same oven temperature profiles, and all 3 models can fit the data very well. So meaning like the data fitting capability of those models are pretty good, right? But what we really care about is what if we change this oven temperature profiles? Not like it goes up and remain constant and goes up. Maybe like we change different temperature profile. So this models can still be generalized to those ANSI boundary temperature profiles. Okay, so then we do some other tests. So if we change the oven temperature profiles, and this is a training scenario, and then we just arbitrarily like create some like the autoclave temperatures, which goes up, remain constant, and then goes up again and remain constant. So this one is not quite different from this one. So you can see our models. You can barely see like the difference between the dashed line and the solid line. So the dashed line is the ground truth and solid line is our model predictions. But you can clearly see the difference for the other 2 black box data-driven models. If we make the things even challenging, and this time we make this autoclave temperature like goes up and remain constant and goes up and constant and goes down and remain constant and goes down. So this one is quite different from our training scenarios, and you can see our models still perfectly fit, right? The generalizability is great for both temperature profile and temperature and degree of Q. But look at the other 2 models; they're just basically completely fail. So especially like for the AECOMP LSTM for predicting the degree of Q, that's completely gave you the like wrong predictions. Okay. So now we still use a lot of sensors. We use like 5x5. So how about we increase the number of sensors, or we decrease or reduce the number of sensors and see what happens? So I made this plot. So basically the horizontal axis is the number of sensors we used for training, and the vertical axis is the testing error for the models. So you can see if we use the tons of sensors, 900 sensors, basically put sensor everywhere, you have a lot of data. So all the models error converge like to very low. Basically, you just fed the data, right? But if you gradually reduce the number of training sensors and to 100 to 20 or even to 1, so other 2 models completely fail because you only have 1 sensors and you cannot train any data-driven, like completely black box data-driven models. But you see, our models still have a very low errors. I can zoom out this region. And so this is our model. So even we have very few number of training data, well, the error still goes up to like less than around the 50%, 15%. But compared to this is like a significant improvement. So if you add like more than 2 sensors, is the prediction will become much better. Okay, so let's make it more practical because in general, like for some physical quantity that are easy to monitor during the manufacturing process, or for some physical quantity, it is not. So in this case, we can easily measure the temperature. We can put a thermocouple right? So it's no problem. We can measure the temperature, but how do you monitor the degree of Q? That is practically not easy or even not possible. So let's see if we only have the temperature sensor and we don't have a degree of Q at all, no measurement for a degree of Q. So in this case, if you want to train models completely in a data-driven way, you can only train a model that make the prediction for temperature, and you cannot predict the degree of Q. You have zero data. So in this case, the two baseline, they won't work. But like I mentioned, the heat transfer and the dynamics, the Q kinematics, they are coupled. And in the sense that we integrate those PD operators into our network. So in general, we can leverage the relation and make the connection. So we can train the models with the temperature data only, and then we can basically predict the degree of Q as well. It's more like a inference of the hidden physics. So this is the result. And for the training that we are going to take the temperature, okay, and train the models. And the after training, or you can test your models on different locations, and you can get the temperature predictions, but also the degree of Q. Those are degree of Q at the center and the corner. So it agrees with the ground truth pretty well. And like I showed you before, I can just change the temperature profile and arbitrarily generate the testing temperature, like open autoclave temperature profiles. So basically the model can be generalizable to those scenarios. You can see the degree of Q and temperature, the time sequence profile looks different once you change the autoclave temperature profiles. But there is some discrepancy, but remember, this is completely testing scenarios. So we are very happy about this result, especially considering that we only include the temperature as the training labels. So we can recover the degree of Q as well. So the good thing of this is because we're trying to learn the operator, so it's mesh invariant or discretization invariant. So it can be generalized to different geometries. So if our sample is not like a square domain and it becomes rectangular, have different aspect ratios, it still can work. And also, like I mentioned, during this training process, because there are some unknown physical parameters we don't know, and we can infer those physical parameters. You can just make those physical parameters as trainable, the same as the neural network parameters. So you can see during this process, those physical parameters, they will convert to the ground truth, which is the red dashed line, during the sufficient number of training epochs. So the heat conductions and ultimate heat reaction of the system and convection heat transfer coefficient can converge to the ground truth in doing this modeling, this model training. All right, so as a summary of this unique feature of this PD integrated differentiable neural models, and it can be trained with partial or indirect label data, and it can work well with very limited measurement, very sparse sensor, and it has much better generalizability in terms of the different geometries or the boundary conditions than a black box model. And it can recover the hidden states, those like the unobserved states, and also like to infer the physical parameters as well. And if you check the comparison with the state of our other black box data-driven model, they have less trainable parameters. So we actually can achieve the performance with much less trainable parameters than the other two baseline benchmark, like the NeuroPDs and AE, COM, LCM. So that means that the training time is a little bit like lower, and also the inference time is lower than the other models. So that's pretty great. So we would like to move forward and think about how can we integrate the real data from Honeywell, from the real manufacturing process. And here I'm going to show you a different process involved in this carbon-carbon composite manufacturing. So in Honeywell's recipe, the chemical vapor refrigeration is very important process, and they will do this CVI cycles for many times and to densify the carbon composite from the preform, from the porous to preform, and so they will kind of deposit carbons. So this process actually involves like the chemical reactions, and this is oven, and they will provide the gas, and those are like reactive gas, and you have the preform, and with like a chemical reaction, they will deposit the carbons and densify the porous preform. So this whole process involves a complex this involves definitely convections, diffusions, chemical reactions. If you want to completely like model this from the physical point of view, that you have to consider the chemical reaction with hundreds of species, and you don't know the reaction rate in general. So it's infeasible, or at least it's not practical, to model such a complex chemical reactions process purely based on the physics. But like I said, we can extract the general the physical laws and build this hybrid differential model, and we still have some data, and then we can kind of train this model without need to bother to like model those those chemical reactions. Most of them we don't have a good understanding, and so in general, this process is nothing but a diffusion and deposition process. And we definitely have this diffusion terms, but what is the effective diffusion rate, which is the spatial temporal field, is not known. Okay, so we have the newer model to handle this, and the C is the molarity of or the concentration of the reactive gas, and here we just treat this as a reactive. The effective gas. So we don't kind of separate out the different species. And this KSV is the effective deposition rate of this reactive gas. So the whole process is deposition and diffusion. Okay, so there's a lot of things we don't know, the effective deposition rate and also the effective diffusion coefficient. We can use the operator learning to learn this operator, because this diffusion coefficient, it's a spatial temporal field. It's going to change over time, and it's related to the porosity field, temperature field, pressure field. Okay, so we can use some neural network to learn the relation between those, basically to learn this operator. Same for the effective depositions, and we can similarly to build this CVI models. So in general, the idea is we encode this diffusion process and those hyperbolic PDs and into this module. So basically, this PD integrated module will learn the transition from about the porosity and from time t to time t+1. So here the t+1 doesn't mean like the numerical time step. It can go a little bit further. So we have the faster inference speed. And also it would describe the transition of the molarity of the reactive gas from t to t+1. So in this way, and we can actually also get weight or mass of my samples. So that allows us to actually integrate the data, like the weight. We can measure weight instead of measure the porosity or the molarity of the gas. Those are usually not available, but it's very easy to get the weight. So basically, if you like in the manufacturing process, after all, we take out the samples and measure the weight and put it in, and we get some like the weight measurements. Okay, so we can use that to train our model. So this is what we did, and we actually used the experiment data from the literature. So what the literature data is, they have those weight information during this manufacturing process, and they basically measure the weight of the samples. And once they cook the sample for a while, they take it out and measure the weight, and you get those sparse weight points or mass measurement. And they do it for different partial pressure of the reactive gas. So this three different color represent three different partial pressures. Okay, so we're gonna use this like data. It's pretty sparse, okay, and for three different partial pressures, and train our models. And then once our model is trained, and we test it on those validation data, so those ANSI data. So those are like different partial pressures. Okay, so you can see this blue, this green and blue. They're kind of like the partial pressure is 7,000 and 10,000, which is kind of within our training partial pressure range. So I would call this more like an interpolation, but it's still ANSI. So the solid line is our model predictions. So it's agreed with the experiment data very well. It's actually captured very well. So for this red one and this black one, it is like the partial pressures is even like out of your training range, which is much lower or much higher than your training range. The model still gave you a pretty reasonable predictions. Remember, we only have those very sparse training data. So those are more like extrapolation. So it has a very good generalizability. And this time is with real experiment data. But so far, I haven't discussed about like the data uncertainty. Because like I mentioned, the model has a model form uncertainty, and neural network has this like neural network model form uncertainty. And also like we try to like assimilate or use the real experiment data, and they have a lot of like data uncertainty, measurement uncertainty. So how can we count for those uncertainty in the model and data? So this is our ongoing work, and we actually extend this primitive models and with a Bayesian learning component that try to quantify and propagate uncertainties. So I don't want to go into those details. So basically, we will use the Bayesian networks and deep ensembles, and to learn the model form uncertainty. And we use the Bayesian network to try to capture the data uncertainty. So in general, we can not only provide a prediction, but also quantify the uncertainties or propagate the uncertainties from data and model to your final predictions. Because here, like I involved a lot of like PD terms. Some of those are nonlinear, so the uncertainty will propagate through some nonlinear terms. So we use the unsanded transform and to enable the uncertainty, like the uncertainty propagations. So it's better to show you like some examples, and with this UQ capability. So this time we'll actually model the CBI process of the carbon-carbon brake manufacturing from Honeywell's. So their process is basically they will go through like several CBI cycles. So they'll go through like one CBI cycles, and they will do the machining and try to like polish the surface. And then they put it back to the oven, and it will cook and densify the samples. And then after the second CBI cycles, you will machine out the surface and move on to the third one. So what Honeywell can give us is just the weight after each CBI cycle. So in general, we have very limited data. So we start from like so first we want to like use the synthetic data to mimic the CBI process. So let me show you the synthetic one and then the real one. So the synthetic data try to mimic the CBI cycle. We first try to make a little bit more training data. So what we did is we take out the sample and we cut it to 3 pieces, and we measure the weight for these 3 pieces. And so for each CBI cycle, you have three mass weight data. And after CVI cycle 1, and you have the machining, and the weight will go down a little bit, and then go to the CVI cycle 2, and you take a sample out and cut it to 3 pieces and measure the weights, and then move on to the next one. So we will have 6. Basically, this is the initial condition, and we will only have 9 weight data to train this model. So it's pretty sparse. So with this, and we can actually know the effective diffusion coefficient, and also the effective deposition rate, and also the molarity and porosity. So those are all like a field. So I only take those are spatial temporal field. It's hard to show you like the spatial temporal field unless I put a animation. So here I'm plotting those physical state on these 2 locations. One is at the corner, one is at the center. So the green one is the center, and the red one is corner. Because here I'm talking about synthetic data, so we know the ground truth. So the ground truth is a dashed line. So because we have very limited data, and you can see our model predictions, this solid line is like a mean, and the uncertainty of my model predictions is like the shaded regions. So it's actually cover the true values pretty well. So even though the mean is not that accurate, but it's still like the quantified uncertainty, this confidence interval can include the ground truth. Okay. So let's make it more like a Honeywell CVI process. So this time I don't cut it. So I just take like the 1 sample. So this time I only have very limited data, only like 3 points. So in this case, and you can see our model prediction can still like fit the data, of course, but you can see a little bit like the stack scattering. That is uncertain because we have so limited, like a very limited number of data. So in this case, the hidden physics we inferred has a large uncertainty, and you have a large scattering this time. Okay, so and that kind of show the reasonable, like the model is pretty reasonable, and now this is still ongoing, and we start to use real data from the Honeywell's manufacturing process. This is like the real weights data, and so far we only cover like the 2 CVI process. So basically for each sample we only have 2 data, and I cannot show you the numbers because expert control. So I can just show you like with even like the more like a very limited data. So our model will give you a large uncertainty, but still it can fit the data and give you a pretty good like weight prediction, but we are more interested in like porosity, molarity of the gas, reaction rate, and because this is real data, we cannot like validate the hidden physics. But Honeywell and us, we are like doing like additional experiment, and we're doing like subscale experiment, and we can even like validate those inferred hidden physics. But this is something I would like to share with you. And as a summary, and in this work, we develop a differentiable neural modeling framework for both partial in null physics and where the both partial in null physics and sparse indirect data are combined to enable a data-driven predictive model. And we demonstrate our predictive model is more generalizable and more data efficient than the other SOTA black box deep learning models by modeling the curing process. And we developed this model for the CVI process as well, and validated it based on the experiment data from literature. And then now we are working on like the extension of the probabilistic differentiable programming, and based on deep ensemble and Bayesian learning to enable the UQ capabilities. And so we also the preliminary result also demonstrate the probabilistic predictive models can model the real CVI process using the real data from Honeywell. All right, so thank you very much, and this is pretty much my talk today. I'm happy to answer any questions.
Thank you very much, Dr. Wang. Do we have any questions?
I have a question. Can I ask?
Of course.
So, you know, I'm not an expert in machine learning, but I have an experience in constructing semi-heuristic analytical models for physical processes. And I'm wondering how this is different from, you know, the regular construction of semi-heuristic analytical analysis, where you basically have a known set of differential equations. You don't know the coefficients of those differential equations. You design a set of experiments which allow you to determine those parameters, and then once you have them, you're completely deterministic, and you can calculate. Yeah. Is it different in any way than this?
Yeah, so this is like a hybrid model. So basically, we don't know the underlying physics. We, of course, like the traditional way to develop like a physics-based model that you can collect some experiment data, and you have some physical reasoning, and you based on some heuristic like analytical relations, and you kind of fit some coefficient and make your model work. So this is like more systematic way. So we're still like training hybrid. So basically we don't know all the physics, and sometimes it's because we don't know the physics, and sometimes we cannot resolve the physics. So there's like a lot of a constellation we cannot like resolve or based on like the practical issues. So in general, we have a very limited data. So how can we deal with these scenarios? So basically, we don't want to use the completely data-driven way. So we actually encode those PD operators into a data-driven neural network. So I'm still talking about neural networks. So it's not like analytical models or PD solvers. So it's you can think this is like the hybrid neural solvers. So the neural network.
I'm just trying to understand in which sense your knowledge about physics is partial. Because in the examples that you have demonstrated, you have full differential equations. It's just the coefficients and those equations are not known.
No. So the examples, what we have done is, for this case, we assume that, so this is for generating the ground truth. But for us, for all these red terms, we don't know. What we know is,
but you do have a general shape of you know that it's a set of chemical reactions. You know that this set of chemical reactions happens according to diffusion and heat transfer equations, and just the coefficients of those equations are not known. So I don't understand in which sense it's not a deterministic understanding of the physical equations, except the fact that the coefficients are not known.
It's not just the coefficient. We don't know this relation as well, and we have the task. We even don't know like this part, this reaction part. So what we encode is just the diffusion, and of course we have some physical understanding of this problem because it's the diffusion, and we know there's a reaction happening. So that is what we can incorporate. That's if you know nothing, then we just go to like a purely data driven. So you still have some idea about the physics. So it's not just like,
to me it looks like a complete physical model. You have in the first equation rate equations for chemical reactions. You don't know. You don't know the rate of the reaction, and you don't know the coefficients of the reaction, but you know that those are reactions of some order.
Yes. We know it's a reaction and it's a diffusion. So what we did is
that gives you a complete deterministic understanding of what's going on, to the extent that you need to semi-empirically measure for one set of experiments what are the parameters that go into that. And then from there, you can basically extrapolate to anything.
So here I want to mention, those are not scalar. Those are spatial temporal field. It's going to change over time.
I see.
Basically, they are also like a field. So they are spatial.
They are not constants. They are not constants. Okay.
No.
That was I was trying to understand. Okay.
Yeah, it's not just to infer the parameters.
I see. Okay.
Yeah.
And you don't even know approximately what are the functional dependencies of those coefficients.
Yeah, we don't know the.
Okay.
Yeah, we don't know the functional definitions. So that's why we need the spatial temporal learning framework. Yeah.
By the way, I'm looking into that reference that you gave, physics integrated neural differentiable model for composite manufacturing. It looks like IU doesn't have an access to this journal online. So if you could share the text.
Yeah, sure. We have a preprint. I can also like share with you like by email.
Is preprint exactly the same as the final paper?
Yes, okay. It's the same. But I can share with you the copy as well.
Because I'm doing material science, so for me, I have a broader interest in this field. Beyond this project.
Yeah, sure. So I'm also like working on like fluid dynamics and also other physical process. And this is a collaboration with my colleague. So I'm not expert in modeling like the material science and manufacturing process, but it's more from the scientific and machine learning side. So I'm happy to discuss with you for other applications or problems. Thank you.
Thank you. And another question that I have, so yes, this is very applicable when you're talking about AC unit, because it's relatively easy to determine the physics that would inform the model. But let's say in general case where you have some kind of machine that is connected to some power outlet and you don't really know everything about the physics that drives the machine, even on the level that you have just described. So it's some of the subsystems of this machine may be thermally driven. Some of the parts of this machine may be consume, air from compressors. Some of them consume, air manifold control or water manifold control that control fluidics of some kind. Basically, like you can't even approximately determine what is the set of differential equations. You maybe know the subset of them. Would that be in any way preferential than just general machine learning training?
Yeah, so I believe like that's a scenario that you only have a very like partial knowledge of the physics, and those can be described by, if you are confident about those physics, those can be encoded as a part of the neural networks, but you have the more trainable part. So you have to rely more on data, because that's just like we need to combine the knowledge and data together. So if we know nothing about the physics, what we can rely is completely on the data. So we have to like admit that. But if we have some partial knowledge, and that will help, that for sure will help if we can encode those partial knowledge, and that will reduce the data. But if the knowledge is too small and we need more data, so we have done some tests. For example, like we have the governing equation, and I gradually like remove those components and assume that we don't know all of them. Eventually, what we have, for example, if we don't know the completely right hand side, we just know it's a dynamics. What I know is du dt and equals to a completely black box, and that will go to the the neural ODE or neural PD. So the completely right-hand side is a neural networks, but you still can encode this. This is like a smooth, like a derivative. So you can impose the smoothness, and that will a little bit help. But it's still like to me that's a black box. That is one of our baseline models in general.
Okay. Thank you.
Okay, thank you. So any other questions? So if no other questions,
yeah, I believe, I don't know, are we over time, Valia, for questions? Or?
Okay.
I mean, I have a couple, but I just want to make sure, I'm not taking up too much time. I just had a simple question about the earlier part where you are showing that once your predictor reaches the extrapolated region, right, and it starts predicting much better than the neural ODEs. Do you think that's because at that point it is essentially solving the differential equation analytically, since you are comparing to the analytical result, right?
So it's not exactly solving like the PD, because it's kind of like a hybrid, solve the hybrid PDs, because it's more like you don't have the completed model form. So you still need to train this neural networks. So you have some part of the PD is actually neural network if you think this from the solver perspective. But the solver is implemented like a neural network. So those like a spatial differentiation is like as a convolution. So it depends on how you view it. So I would say it's more like you actually train those hybrid neural solvers and to match the data. So that's why like once this is trained and it can work like a solver.
So will it actually end up failing if I continue the time forward? Because we never saw the case where it actually starts to predict poorly as time was, You believe that at some point it actually will fail, or will it always be, refitted to the ground truth because of you're using that differential of operators, right?
So yes, I think because they still have the data-driven component, so you can still see the error accumulation. I would see, for example, I think this is more clear.
Yeah, here, yeah.
So the error still goes up a little bit, but the rate is much lower than this one.
Exactly. So the point is, the reason why the error is so small, is it because at some point it has essentially learned the partial differential equation exactly? You know what I mean?
Yeah, I think so. That's my hope. So basically, I would like to learn this operator. So you are right. If we can learn this missing terms, and also learn the schemes, numerical schemes, and if this learned stuff like is like an operator, and it can be generalizable to like the very even they can be propagated for longer term. It's without any problems. But most of the time, I shouldn't say that we're actually learning we have learned the operators. So I think because you structure the learning or the neural network in this way, you are more likely to learn the operators than the complete black box, because the black box is too flexible. So you can easily fit the data, but you cannot guarantee the predictions is also good in the extrapolation range. So that's my.
And Vikram, I think this specific example is not a very good one because the behavior here is periodic. So if you hit, if you hit the period and phase with what you trained your neural network, you will forever stay in the range.
Yeah, but you see the neural ODs don't, right? The other
but even for so even for this periodic behaviors, if you use the black box and let the black box to build this next step model, it will show the error accumulation. Yes, you're right. We actually test this on transport.
But the question is, if you tell the black box just that only thing, that the solution is periodic, will it be able to replicate the results with the same? So, like the physics that you learned from here is that the process is periodic. This understanding is enough in order to predict the behavior almost in full.
I think here is not exactly periodic, so I can enforce like the periodic boundary condition for the complete purely data driven. But how do you tell the data driven it has periodic behaviors? And this is actually the way how can we actually leverage the prior knowledge and build into the neural network. If we have some way that tell the pure data driven, okay, this is more like periodic behaviors. And you kind of impose some physical prior because you understand this is periodic flow. And if you embed that, I believe that will improve the performance. But the thing is, how do we incorporate those constraints? That's a problem. Yeah.
All right. Thank you.
Okay. Thank you.
No more questions from us, so I think we're good.
Okay, great. Thank you. So maybe like we just stop here. Where is our host?
Yeah, I don't know. Palia, are you here?
Okay, see you guys later. Thank you for the interesting lecture.
Okay, all right.
Thank you so much.
Thank you.
Bye.
Bye.